Hello everyone, I'm Sizhe Ma from Carnegie Mellon University. Today on behalf of our team of three, I'm here to present on Towards Standardized and Autonomous Predictive Maintenance, a Unified Digital Twin Framework, and Autonomy Level-Based Roadmap. And as you might notice from the subtitle, this presentation will cover two pieces of work that we submitted to DTPI this year. So, to start with, currently the digital twin are gaining a lot of prominence across these diverse fields like manufacturing, energy, and infrastructure, and at these different levels, including individual level, fleet level, or all the way up to like strategic level. And among these different applications, predictive maintenance has always been on the frontier of all these different applications. And in general, predictive maintenance is defined as this process that monitors actual equipment condition using data to schedule maintenance activities based on need and prevent failures. And at the bottom, we have a standardization effort that defines different tasks in predictive maintenance as different modules. The predictive maintenance pipeline often starts with these data acquisition and data manipulation steps, and it soon enters the three pillars of predictive maintenance. Basically, in order for any task to be called predictive maintenance, it needs to have at least one of these three pillars. And in some contexts, they're often also referred to names like anomaly detection, diagnosis, and prognosis. And once the insights from these three modules are being generated, they are going to be inputted into the downstream to generate things like recommendations or decisions. And this is actually not the only well-known standardization efforts in predictive maintenance. And thanks to all these standardization efforts from these different organizations, predictive maintenance is able to grow from merely a definition more than 2 decades ago to these current industry-level solutions already implemented by many organizations throughout these routes or anchor points. However, if you look at the side of digital twin, you realize that the lack of corresponding standard is actually hindering the transition of predictive maintenance digital twins from a research level promise to an industry level practice. And just last year, the National Academy of Engineering published a report on digital twin, which could be viewed as this white paper that on a very high level defines digital twin and highlights some of the state-of-the-art challenges and their potential solutions. It mentioned basically what we just talked about, which is this lack of agreement on digital twin made it very hard to distinguish what is merely aspirational and what is a true digital twin. And to solve this problem, the NAE report provides a very high-level foundational blueprint for digital twins definition, and some of which components include like physical counterpart, or the physical to virtual data flow. Although this is not really an implementable framework that they proposed, the report also identifies these 5 key features for developing or evaluating any digital twin solution. For example, let's find a less self-explanatory one. Let's say modular structure. So basically, modular structure ensures the digital twin applications can be upgraded and scaled without overhauling the entire system's interoperability. And this is actually such a call to action towards our digital twin community because in order to realize the full potential of digital twin, a more integrated research agenda is now required on these foundational elements that the NA report highlighted by incorporating some domain-specific needs. And this is what we're going to do in this work. We aim to advance the effort through 2 foundational steps, supporting both interoperability and standardization. And on the left, we have these existing standardization efforts for digital twin. And on the right-hand side, we have these existing standardization efforts for predictive maintenance. So our first step, related to our first research objective, aims to advance the foundational elements in the NAE report to a more implementable digital twin framework that supports consistent development, deployment, and evolution. Once the first step is done, we'll move towards our second step, which is to develop a progressive levels of autonomy, starting from manual through automation and all the way to final autonomy. So within this two-step process, the framework itself, from the first step, is like the foundation that bridges the digital twin and predictive maintenance, while the second step, related to the level of autonomy, is like the guiding rail of the bridge, to make sure that the predictive maintenance digital twin is always developed on track without the possibility of developing off the autonomy roadmap. And so let's start by looking at the first research challenge, or the first research objective. So among further reviewing these existing digital twin frameworks, we realized that many of them actually fell short, often lacking one or more critical features from the NAE report. And that's why in the next few pages, we'll progressively introduce the digital twin framework that we developed, aiming to offer a comprehensive understanding of the framework while giving you an idea of what is our thought processes when developing this framework. And in the meantime, to help contextualize, we offer a predictive maintenance task on New Osipin Bridge, which is a bridge located on CMU campus, as an example to basically talk about what are each of these components manifest into within a real-world predictive maintenance digital twin example. So to start with, we introduce the physical and digital counterparts. So let's look at the left-hand side first. So the physical asset is the real-world system under observation and control. They form this foundation of any digital twin. So without the physical asset, the digital twin becomes purely hypothetical with no real-world impact. And right next to it, we have the hardware interface, which can be seen as this conduit that linking sensing and actuation devices to the broader system. So without it, the digital twin becomes an isolated software model. And on the right, we have the digital twin, which acts as this replica of the physical asset through the information model and simulation engine. So here, the information models and simulation engines are designed to update each other, just like how components and behavior of a physical asset are impacting one another. So right next to it, we have the software interface, which provides an operational layer that automates data exchange and user interactions. So without it, queries can of course still be done manually, but the problem is that this case-by-case nature significantly makes it difficult to aggregate and distribute data efficiently and accurately. And this is actually going to ultimately limit the whole system's scalability. And within our contextualized example, the physical asset is the bridge itself, while the sensors are these accelerometers measuring vibrations, and actuators are still human, as the downstream insights generated by the digital twin are still recommendations that require human actions. And for the digital twin, the information models include these CAD drawings, while the simulation engine includes these finite element analysis model of the bridge itself. And in the next step, we further introduce these bidirectional interactions between the physical asset and the digital twin, where the upstream input of digital twin is often sensor data, while the downstream output of the digital twin is control input towards the physical asset. So in the illustrative example, the sensor data is often these multi-channel time domain signal, while the control input is different kinds of decisions, like whether we want to perform inspection or maintenance on the bridge like today or tomorrow. And in the next step, we further introduce these components related to the management of data flow and history, such as, let's say, middleware. So middleware is basically this coordination layer that continuously channels real-world data among all other components of the digital twin framework. So it ensures there is a unified flow of information, because without a middleware, the digital twin becomes a disjointed ensemble of isolated models. And basically it's unable to maintain the synchronized data exchange across different modules. And in fact, existing solutions in literature often implement these ad hoc solutions here, such as these customized scripts or these user in loop that rarely scale well. And another component we introduce here is the historical repository, which is an external storage system that archives these past operational data and often provide a time index record of how the system evolve over time. And its digital, it also often documented its digital counterparts evolving situation. And without the historical repository, the digital twin is basically unable to learn from previous states or project into the future. And within the illustrative example, the middleware could be a MQTT broker that basically delivers different input into different repository depending on the subscription conditions. And the historical repository, on the other hand, could simply just be an SQL structured database. And in the next step, we further introduce the downstream components related to workflow analysis, known as the workflow and analysis algorithms. And so this is basically the decision-making center of the whole framework. They take care of how incoming data is processed and transformed into actionable insights. And without it, the digital twin is a static repository of information. And it's not able to generate this predictive or prescriptive insights. And within the workflow analysis algorithm, we have the observe, orient, decide, and act loop, or also known as OODA loop for short. So the OODA loop serves as this high-level breakdown of general decision-making steps of all workflow analysis algorithm that can be instantiated. So basically what that means is that the OODA loop can be designed to support modular upgrades in each phases. It allows these advanced analytics or machine learning to improve either the orientation or the decision accuracy without overhauling the entire chain of operation. And in the contextualized example, the OODA loop manifests into the following process. The module first observes the time series data which helps us orient the health status of the physical asset. And then based on the status of our asset, we'll evaluate different decisions and decide which decision we want to further act on the physical asset. And in the end, we introduce the interactive exploration step through query and responses. So query and response is like a structured mechanism for requesting, obtaining specific data or analysis from across the whole framework. So without a flexible query and response mechanism, the digital twin can only be used for a pre-specified set of use cases. Essentially, it downgrades to a cyber-physical system. And in addition to that, the module also supports a what-if loop for scenario exploration. Basically, it allows the framework to iterate between query and responses to refine possible strategies before you actually act on any of those strategies. And within the illustrative example, the what-if loop helps us identify these outcomes of different decisions, like what if no maintenance is scheduled today, or what if there is a maintenance scheduled today. So this helps us to evaluating the outcome of decisions before you even act on it. So this is the material about our digital twin framework. And now we'll discuss the guiding rail of our bridge, which is our second research objective. So to reiterate a bit, our second research objective is to construct a structured, progressive pathway towards autonomous predictive maintenance using digital twins. So this is quite a long objective, so let's explain some of the keywords here. So start with what is a structured pathway? So this actually refers to one of our earlier work where we synthesize these informational and functional requirements across domains to define the structured and standardized predictive maintenance pathway. But what are these informational and functional requirements? So informational requirements represent what the process must know. For example, the third information requirements, or called R3, is contextual information. Basically, it refers to those information that's collected not directly from the asset, but they're still going to be used to help making decisions or generate decisions. These information would include things like sensor-related information or environmental data. And on the other hand, functional requirements represent what the process must do. For example, FR1 is theory awareness. It represents the system's capability to make decisions not only based on the data itself or statistical insights, but grounding these consistent physical representations as well. So that's enough context about a structured pathway. But what is a progressive pathway? So this progressive pathway is actually what we draw inspiration from autonomous vehicle field to create these levels of autonomy for predictive maintenance. So this is because since its creation, the levels of autonomy framework in autonomous vehicle has been guiding their development for over a decade. Basically, they create this common ground for different stakeholders to align their expectations. And this is the level of autonomy framework that we developed for predictive maintenance, and we'll cover them more detailedly in the next few pages. So, since we now have a much better understanding about some of these words like structured or progressive, we might have another question. What do we mean by using digital twins? So this work basically aimed to map predictive maintenance requirements to levels of autonomy with digital twin capabilities in the middle, bridging informational and functional requirements. So in another word, as digital twin is considered as a lifecycle tool that could be developed incrementally across different stages of their life cycle, we want to use them to fulfill more and more requirements through different life cycles and to help predictive maintenance system to climb the autonomy ladder on the right. So since we now have a full understanding of this objective, we can now start to look at this pathway more specifically. And similar to the previous illustrative example, here we'll use the same example to help contextualize different stages in a real-world context. So to start with, we have level 0, which is no automation. So basically at level 0, all of the predictive maintenance tasks are carried out fully manually. And in this level, since there is no automation, the system does not need to really do anything on its own. So basically what that means is only information requirements are related. So basically 4 of them are related, including physical property, reference values, historical data, and fault data. And in the illustrative example, the first level is often related to the initial stage of digital twins lifecycle, such as the conceptual design phase. And in this phase, the informational requirements and contextualized to things like the bridge dimensions or past project data, and all of which they're going to be stored within the information models themselves. And when we reach the second stage is where we reach assistance automation. So within assistance automation, basically only one predictive maintenance function is automated, and humans still control over the most of the decision-making process. And at this level, since the digital twin, like we said, is developed incrementally throughout its life cycle, we will also develop its requirements incrementally. So what that means is on top of the 4 requirements from level 0, we'll have 2 additional requirements marked in red, which are the contextual information and theory awareness. So in the illustrative example, this is where we enter the more detailed design phase. The newly added requirements will further manifest into things like site-specific data or finite element analysis. So site-specific data could further help with more detailed site-specific simulation, while finite element analysis could help with updating the design models and the simulation-based simulation engine. And within level 2, this is where we enter partial automation. And at level 2, basically now multiple tasks are run automatically, with humans only overseeing the system output themselves. And in this step, 3 of the newly added requirements are performance matrix, referring to these performance of operations of an asset or its components. And context awareness basically refers to this ability of digital twin to make decisions not only based on the asset, but based on the context the asset is in. And interoperability refers to the ability to generate human understandable decisions. And this is where we enter the construction and commissioning monitoring stage of our physical asset. And IR4 contextualized to progress tracking matrices, which is going to use the OODA loop to help generate decisions, while context modeling is used to fulfill FR2 that guide both the downstream OODA loop and the simulation engine itself. And FR3 is fulfilled by a dashboard through software interfaces. And in the next stage is where we left the domain of automation and finally enter the domain of autonomy. So at this level, the system autonomously manages these normal cases or these moderate anomalies, but still hand over unusual or extreme conditions to human operators. And at this level, we further introduce two functional requirements, including robustness, which is this ability for system to handle faults like input-output error or out-of-boundary data, while adaptivity often refers to the system's ability to handle concept drift. And in the illustrative example, this is where we enter these early phase operations. And this refers to these initial phases right after construction and commissioning, and this is when data is only open to public but still under close observations. And from time-wise standpoint, this is usually the first 6 to 24 months after the construction is done. And basically, FR4 changes to these fault and error tolerance mechanism that's going to relate it to the communication infrastructures of the digital twin. And FR5, which is adaptivity, is going to manifest into this concept drift detection mechanism and adaptation mechanism, which is going to help both the downstream decision modular and the simulation engine itself. And at level 4 is where our system enters the phase of high-level autonomy, where now the entire predictive maintenance workflow could be handled autonomously, with human only intervening on very rare situations. And at this level, we further introduce two functional requirements, which are scalability, which is this ability for system to scale up and down, and transferability, which is this ability of the system to transfer knowledge from a source to a target domain. And in the illustrative example, this is where we enter the mature routine operation. So basically, this will represent the long-term steady-state operation of the bridge, and this is normally 2 years after commissioning. And FR6 is now represented by the scalable data management of the communication infrastructure and different data repository. And FR7 manifests to this deep transfer learning mechanism for both the downstream design module and the simulation engine itself. And in the end is where we entered full autonomy, which now all functions, including the critical fallback, are fully automated, with no human oversight required for these standard operations. And although this sounds very much like a vision at the moment, it is still critical to define them because this helps us to understand where we're ultimately heading towards. And at this stage, we further introduce the last functional requirements, which is uncertainty awareness, or known as this ability of the system to handle uncertainties. And this is where we enter the advanced operation in our case study, where we now might want to make decisions based on, for example, the human walking patterns on this pedestrian bridge. So this is where the uncertainty quantification kicks in to make sure both the digital twin and the downstream tasks are either updated or predicted based on some uncertainties. So this is basically all about our second contribution, which is the levels of autonomy roadmap. And so now let's look at some final takeaways. So first of all, our framework offers a structured blueprint for building a robust, standardized digital twin. And second, the Levels of Autonomy framework provides these practical roadmap to systematically advance predictive maintenance capabilities. Thirdly, digital twins enable the progressive fulfillment of autonomy requirements, guiding the development of truly autonomous predictive maintenance. And that's all for my presentation. Thank you.